Okay, now that we have covered the types of loads that buildings are designed for, and talked a little bit about the general process of designing a structural system, I wanted to dive deeper into how structural engineers actually trace loads through a building. And this example is going to go into specifically how we trace loads from beams to girders into columns. This example is going to be pretty high level, not very detailed from the perspective of a structural engineer, but will certainly be more detailed than what would be required for an architect. So your homework problems and your exam problems will not be as complicated as this, but I figured it's always best to be more detailed in the lectures so that you have everything that you need to do the homeworks and exams. So for this example, we are going to be using the same pretend steel set of drawings that I've been using in past examples. And we are going to, as I said, take down some loads for a typical roof beam, typical roof girder, and a typical column. For the sake of this example, we will say that the building is located in Boston and that the occupancy is retail on all floors. So let's get started with laying out the loading criteria for this building. And this is the information that would be placed on the general notes page, the first page of the structural set. So let's start with the roof loads. Of course, on the roof we are going to have some dead loads. The self-weight of the structure itself, which includes the beams, the girders, the columns, and the decking, will be our first category of load. And for this, we will say that the roof deck is going to weigh about 2 pounds per square foot, and the steel framing itself will be about 10 pounds per square foot. Of course, we could get the exact loading from the set itself by looking at the weight of all of these steel sections. But for now, we're going to assume that the building hasn't been fully designed yet. And in fact, at the beginning of the steel design, we would of course not know what any of these sections weigh yet. And so we would have to have some kind of allowance for the self-weight of the structure. And this 10 pounds per square foot is generally pretty conservative for a steel roof assembly. In addition to the self-weight of the structure, we also have all of the MEP equipment, the finishes, the ceiling, all of the architectural components and whatnot that will be permanently installed within the building. So we call that a superimposed dead load. So on a roof you will typically have some kind of fiberboard or substrate material, rigid insulation, perhaps more fiberboard, a weather barrier, all that kind of stuff, all assembled on top of the roof deck. And also, the superimposed dead load includes all of the stuff that's hung just below the floor level. So that includes the MEP, the hung ceiling, if there happens to be one, which could be your typical acoustical ceiling tiles or gypsum board, etc. Also, lights have weight and they're hung from the structure, so that will all be included in the superimposed dead load. And the allowance that we typically give for superimposed dead load is about 15 pounds per square foot. So altogether, the self-weight here will be 12 pounds per square foot, and the superimposed dead load will be 15 pounds per square foot. And so our total roof dead load will be 27 pounds per square foot, or we'll just round that up to 30. Again, to be conservative. So our roof dead load, we will use 30 pounds per square foot. For our floor load, on the other side here, in addition to the deck, we now have concrete poured on top of the deck. And that concrete has a significant amount of weight to it. So over here, this concrete and deck will weigh about 70 pounds per square foot, and floor framing tends to be a little bit heavier than roof framing, so we'll use 12 pounds per square foot, giving us a total of 82. superimposed dead load, we'll still use the same 15 pounds per square foot allowance for all of the hung MEP and architectural finishes. So that gives us a total of 97 pounds per square foot, and we'll round up to 100. Next, for our loading criteria, we have our live loads. And for the roof, we have a code-prescribed minimum roof live load of 20 pounds per square foot. And that 20 pounds per square foot is intended for maintenance workers, so people who are maintaining the rooftop equipment or the roof assembly itself. That 20 pounds per square foot allowance is not intended for any kind of public assembly live load. So if you are intending to design a roof for public occupancy, say a green roof, you would definitely need a higher roof live load than 20 pounds per square foot. But for this building, we are going to assume that it is not open to the public on the roof. Of course, the rest of the floors in the building will be open to the public, and they are retail occupancy. And so, given this retail occupancy, we will turn to Chapter 16 of the IBC and scroll down to our live load tables, which start in section 1607. And we will look for an occupancy that matches ours. If I scroll down here, see we have stores. Retail first floor is to be designed to 100 pounds per square foot minimum, and upper floors are to be designed for 75 pounds per square foot minimum. Now let's say we want to design all the floors to the same live load criteria. This will help simplify the design and also give the owner a little bit more capacity to their building. So let's design all of the floors to 100 pounds per square foot live load. And it's important to note here this little footnote N. And you can see that there's this footnote on basically every load that is over 100. So if I scroll down to the footnotes here, it says that live load reduction is only permitted in certain circumstances. So, if you have a live load that is over 100 pounds per square foot, that generally will mean that you are not allowed to use live load reduction. But if you are at 100 or below, you are permitted to use live load reduction. So in this case, since we are using 100 pounds per square foot, we will be able to use live load reduction. So that's something that's important to keep in mind when you're designing your buildings and determining the occupancy. So if you tell a structural engineer that you want to design a building for a certain occupancy, and that occupancy happens to have a code minimum requirement over 100 pounds per square foot, that means that the structural engineer will not be able to use live load reduction, and you will likely end up with a much larger structural system. Next we have our snow load. Snow load is of course determined by the location of the building, which we've decided will be in Boston. So to determine the snow load on the roof, we turn to this ASCE 7 document, and we go to the snow loads section. And from here we scroll down to the maps. And you can see here that this map, this figure 7.1, says ground snow loads, PG. So ground snow loads are not the same as roof snow loads. However, they are related. So if I scroll back up to the top, you can see that there's a formula here for determining the flat roof snow load, PF. And you can see that it is equal to this factor 0.7 times these other variables times the ground snow load. And each of these factors, the exposure factor, the thermal factor, and the importance factor for a typical building will be just 1.0. So the only factor that we really need to pay attention to is this 0.7. So we're going to take the ground snow load and reduce it by 30% to get our roof snow load. So scrolling back to the maps, these can be pretty difficult to read, but if I zoom in on Massachusetts, I think it's pretty safe to say that we are somewhere in this 40 pounds per square foot region. And so that is our ground snow load. Now it's important to note that depending where we are in Boston and what neighborhood we are in, there could be a local requirement for a higher ground snow load. So something higher than 40 pounds per square foot. And that local code jurisdiction will control over this IBC reference standard. But for now, we're just going to use 40 pounds per square foot for our ground snow load. And as I said, we will reduce that by 30% to get our flat roof snow load. So we end up with 28 pounds per square foot for our snow load. So now we have our full loading criteria laid out for this building, for the roof and all of the floors. For the roof, we will use 30 pounds per square foot dead load, 20 pounds per square foot roof live load, and 28 pounds per square foot snow load. For the floors, we will use 100 pounds per square foot dead load, and 100 pounds per square foot live load. So with that loading criteria in mind, let's now trace these loads through the structural members, starting with the roof beams. And you can see I've picked out a typical roof beam here in the middle. So as we saw in the previous video, the tributary width of this beam is going to be equal to the beam spacing. So there are 3 spaces here between grid lines 2 and 3, which means that the spacing of the beams is 20 feet divided by 3. So the tributary width is 20 feet divided by 3, or 6 foot 8. Now we said that the dead load here was 30 pounds per square foot. We multiply that by the tributary width of the beam, and we get 200 pounds per foot for the linear load across this roof beam. Next we have the roof live load, 20 pounds per square foot, multiplied by the tributary width, and we get 134 pounds per foot. Finally, the snow load, 28 pounds per square foot times 6.67 equals 187 pounds per foot. So now that we have all of these individual loads according to their type, dead, roof live, and snow, of course we need to combine them into an ultimate load to design this beam. So for that load combination, we turn back to the IBC, section 1605, and we look here for the load combinations for strength design or load and resistance factor design, LRFD, which is how we design steel and concrete members. And we're going to look for a load combination that we think is going to provide the largest load, the maximum load, to design the member for. So first we have this 1.4 dead. That could be the maximum load, however there is no live or snow involved in this equation, so it's pretty unlikely that this load combination is going to control. Next we have 1.2 dead plus 1.6 live plus 0.5 roof live or snow. So this one may be our controlling load combination, but this 0.5 seems to be a pretty low factor. So let's look at the next one. Next we have 1.2 dead plus 1.6 roof live or snow. So this load combination uses both dead and either roof live or snow combined together. So this load combination seems like it is going to be our controlling load combination. It's It's important to note here that it's either roof live or snow. And that's because, if you think about it, if there is a maximum amount of snow on the roof, 28 pounds per square foot, it's pretty unlikely that you're also going to be sending up maintenance workers onto the roof. And so that's why this load combination is either or. You either have the maintenance workers up there, or you have your maximum snowstorm. It's also important to note, as I said in the previous video, that the dead load only gets an increase of 20% because we're pretty confident about the assembly for the dead load. However, snow load and maintenance worker load is pretty unpredictable throughout the entire life of a building, and so we increase those loads by 60%. So our ultimate load combination will be 1.2 dead plus 1.6 roof live or snow. Of course, in Boston, our snow load ended up controlling over our 20 pounds per square foot code minimum roof live load. And so we will use snow in our load combination and leave out the roof live load. So we have 1.2 times 200 pounds per foot plus 1.6 times 187 pounds per foot. And all of that comes out to 540 pounds per foot. So for every foot along this beam, there will be 540 pounds of load. And that load is what we need to design this beam for. Now, moving on to the roof girders. For the girders, of course, they will be receiving the load from the beams. And so rather than having a linear load across the member, we will have point loads in two locations. And it's important to note for an interior girder like this, it will receive load on both sides. So the load will come from the beam on both sides of the girder, and it will be half the load that it receives. The other half will go to the girder on the opposite side. But in total, it will receive 10 feet from this side, 10 feet from this side, and so in total that will be 20 feet of load. So if we go back up here to our roof beam, we saw that there was 200 pounds per foot of dead load. So 200 pounds per foot of dead load times 20 feet, that gives us 4,000 pounds, or 4 kips. Next for roof live, we had 134 pounds per foot times 20 feet. That gives us 2.7 kips. Snow, 187 pounds per foot times 20 feet. That gives us 3.8 kips. Now for our load combination, we have very similar loads here, and so our controlling load combination will likely be the same. 1.2 dead plus 1.6 roof live, not plus, or snow. And again, it's the snow load that's going to control. So now we calculate the ultimate load on this girder. 1.2 times 4 kips plus 1.6 times 3.8 kips. We end up with about 11 kips. And note that that is 11 kips here and 11 kips there as well. So that will be the load on the typical roof beam and typical roof girder between lines 2 and 3. Of course, getting the loads for the other beams and girders would be a very similar process, and similar process for the floors below as well. A lot of this work is not particularly difficult, it's just very tedious, and you have to make sure that you're keeping track of everything. And so that's why we usually use computer programs to do this for us. But we do still occasionally use hand calculations in a few key locations to verify that the computer has kept all of the numbers in line correctly. Now finally, let's take a look at a column. And here you can see I have the level 1 floor plan, because we are actually going to be taking the load all the way down to the foundation. So, if you can recall in the set, each of these floors looked basically the same. There were no column transfers or anything like that. This is a pretty simple building. And so the tributary area for each of these columns is going to be the same on each floor. And we are going to have a roof level, 3 total floor levels, and then the basement. The loads from the basement, however, are going to go straight from the slab on grade and into the soil, so they don't interact with the column at all. So it's only this first floor level, levels 2 and 3, and the roof that will pass load into our column. So with that said, let's take a look at a typical column. The tributary area, of course, as I said in the previous videos, is going to be halfway to each adjacent column. And it's going to equal 15 feet plus 10 feet times 10 feet plus 10 feet. 500 square feet. So now the dead load on the roof was 30 pounds per square foot times 500 square feet. The dead load on the floors was 100 pounds per square foot times 500 square feet, and there are 3 total floors. So that gives us 165 kips. Next, for roof live, we have 20 pounds per square foot times 500 square feet. Of course, there is no roof live on the floor levels, so this gives us 10 kips. Snow load, 28 pounds per square foot times 500 square feet equals 14 kips. So the snow load, again, is going to control over the roof live. Now floor live load, 100 pounds per square foot times 500 square feet. And recall here that we are permitted to use live load reduction. And we calculated previously that the live load reduction factor was 0.44. And so we will apply that factor here. And of course we have 3 floors that we're designing this column to hold. So that gives us 66 kips. Now for this column, we have both roof live load, snow load, and floor live load that we need to combine into an ultimate load. So let's look at our load combinations again from the IBC. And we can see here that we have 2 options. Either 1.2 dead plus 1.6 floor live plus 0.5 snow, or we have 1.2 dead plus 1.6 snow plus 1.0 live. This F1 factor is going to be 1.0. So, either we apply the 1.6 to the floor live or to the snow load. Let's take a look. Given that we have a floor live load of 66 versus a snow load of 14, our ultimate load is going to come from applying that 1.6 to the larger load here, the 66. And so our ultimate load combination is going to be 1.2 dead plus 1.6 floor live plus 0.5 snow. So that gives us 1.2 times 165 plus 1.6 times 66 plus 0.5 times 14. And again, we're using the 14 because our snow load controls over the minimum roof live load. So in total, our ultimate load for our column is going to be 311 kips. So to summarize, for our typical roof beam between lines 2 and 3, we had 540 pounds per linear foot of ultimate load. For our typical roof girder between lines 2 and 3, we had ultimate loads, 2-point loads, of 11 kips. And for our typical column at the foundation level, we have a load of 311 kips. And that is how we trace loads through a building. Again, from a structural engineer's perspective, this is a very general, high-level load takedown. But from an architect's perspective, this is well above and beyond what you would be expected to do. But I think it's helpful for you to know exactly what a structural engineer is doing as they are going through their process of designing your building. And so we're going to continue to dive deeper into that process next week when we discuss lateral loads. So as always, I thank you for your attention. Good morning, good afternoon, and good night, and I'll see you next time.